From ContainerDays Hamburg, this video is proudly presented by Dux IT.
Thank you for joining my talk. Today I want to showcase a technology which is called Kubenix, which enables us to find our Kubernetes workloads in a fully reproducible fashion. If you like to follow along, feel free to scan this QR code here or use the link provided. Before we get started, let me briefly introduce myself. My name is Arik Grahl, and I'm a senior software engineer at Sys11, a cloud service provider based in Berlin. At Sys11, we operate several data centers in Germany, and we benefit from our own network infrastructure. At the core is our OpenStack-based cloud offering with a managed Kubernetes on top of it. Within my team, we built the highest abstraction layer for end users, which is a software supply chain management system that handles application lifecycle management on top of our infrastructure. My day-to-day business involves developing Kubernetes controllers in Golang and, of course, packaging with Nix. If anything in this talk sparks your joy, feel free to contact me via any of these channels here. I'm always happy to chat. As you know, Kubernetes at its core is a distributed operating system. Under the hood, it relies on Golang types and protobuf for defining objects. But for most end users and operators, what we actually interact with is an API, which speaks JSON and far more commonly YAML. YAML is a great transport for APIs. Format for these APIs. However, using YAML as a source of truth for complex infrastructure brings its own set of challenges. Especially for complex documents, it becomes pretty evident that it's very verbose and quite repetitive. It's not easily possible to extend the document and organize it into fragments. The provided constructs for abstraction and reusability are not sufficient enough, which result in challenging inheritance. Type safety is weak, so confusing type errors can occur. And these issues only grow as the system scales. Of course, none of this is news to anyone who worked with Kubernetes more than 1 week. In response, the ecosystem has sprouted a variety of tools for generating YAML and JSON. JSONnet, Customize, Helm, Helmfile, you name it. But a critical observation, most of these tools don't solve the underlying problem with plain YAML. Instead, they offer mitigation strategies, essentially layering more abstraction and indirection on top, often introducing entirely new classes of issues. It's a bit like patching leaks in a boat instead of building a better one. Among these tools, Helm has emerged as a de facto standard for packaging and deploying applications in the Kubernetes ecosystem. Whenever there's a cloud-native application, chances are incredibly high that you will find a Helm chart. It even offers some rudimentary dependency management for referencing downstream charts. However, at its core, it's simply a templating engine built around Golang's text template library. While technically sound, this approach essentially means we are templating a structured language, which is more error-prone than it appears at first. This has 3 consequences. Let's look at a typical Helm template. You'll notice heavy use of prefix conditionals, which can be confusing at first glance. Even more challenging, templates sometimes enforce configuration validation at render time. That's mixing validation with presentation, making things even harder to debug. YAML fragments are scattered throughout the template, and without any schema validations, it's way too easy to make a syntactic mistake that only shows up much later downstream. Injecting values also requires carefully managed indentation, introducing a whole class of errors. Perhaps worst of all, those if conditions often span the entire file, sometimes hundreds of lines of code, making it far too easy to forget an entirely end or an entire logic branch. So over the time, your template resembles a bowl of spaghetti. Luckily, we can do better. Let me introduce you Nix, the basis that powers Kubenix, and a real solution to many of the problems we've just seen. With Nix, we can make systems that are reproducible, declarative, and reliable. Now, before we go further, let's clarify terminology, because Nix can refer to several things. First, there's NixOS. It's a functional Linux-based operating system built on top of Nix packages. It's immutable by design, and upgrades are atomic and reversible. Then, second, there's Nix packages, the package manager managed via the Nix language. But Nix packages is at the same time also a large monorepository. In fact, with 100,000 packages, it's even one of the largest in open source. It includes all dependencies for a complete and self-contained build chain. And at the heart of everything, Nix, the domain-specific language. It's a purely functional, lazily evaluated language which is designed for the Nix package manager. Since the language Nix is central to Kubenix, let's explore some of its features. We start with the ones which are related to its functional nature. The first property is that every valid piece of Nix code is an expression that returns a value. So, for example, a string literal is an expression that returns a string. Same for more complex expression, an attribute set which holds the string from before at the key x. Again, whenever evaluating this expression, its value is returned. The second property of a functional language is that evaluating a Nix expression will always yield a data structure. To illustrate this, we are defining a function f, which receives an argument x and returns it as it is. When calling f with the string as the argument, for instance, this function evaluates and returns the respective data structure. We now call the same function f with a different argument, for instance, the attribute set from the example before, and we receive the passed data structure. This illustrates as well the concept of parametric polymorphism, as we can pass different types of arguments to the very same function. Generally, Nix is strongly typed, but dynamic, meaning types are checked during evaluation time and later on strictly enforced. The last important property of the functional language is that evaluation does not execute a sequence of operations. Let's define a variable x with a certain value and another variable y, which depends on this variable. When evaluating, we get the expected result based on both variables. However, we can also define y and x in a different order. When evaluating y now, we get the same value and no error whatsoever. So, Nix is about describing data and relationship between data, not about executing steps in a sequence. Another key property, Nix is lazily evaluated. This means nothing is actually computed until it's needed. To illustrate this, let's define an attribute set with two keys, one holding an exception and another key or well-known string. If we evaluate the key x of the attribute set here, Nix throws an exception as expected. However, for the exact same attribute set, when we evaluate the key y, we successfully get the respective value without any errors. So, lazy evaluation helps us avoid unnecessary computation and makes composability much easier. Last but not least, Nix is a purpose-built language for system packaging. This means that a real Nix expression in Nix packages, for instance, usually returns a so-called derivation. These derivations can often be encapsulated by a higher abstraction, providing some language-specific common builders, like for instance here for Golang. If we want to build the command line to kubectl with Nix, as a common Golang example, we would specify the package name, its version, and the subpackages we are interested in building. We can then provide the necessary source code from GitHub, which is identified by an owner, repo, and the Git revision, and everything is guarded by a hash. This is all it takes to package a binary with Nix, thanks to its rich utility functionality. You're not intended to understand this example in this, it just should give you a rough idea how Nix is used in the real world and to illustrate its role as a purpose-built language. Now that we understand what makes Nix so compelling, let's zoom in on Kubenix, the bridge between Nix and Kubernetes ecosystem. Kubenix leverages the power of NixOS modules to define Kubernetes manifests, giving us the advantages that go far beyond what templating tools can offer. Why is this so exciting? For starters, boilerplate code is slashed. There's no more endless copying of YAML. We get true type safety. You get early feedback if something is breaks and doesn't match the expected schema. Composability and inheritance. Nix language feature let you abstract, extend, and override configuration with ease. And also first-class integration. Kubenix makes it trivial to pull in Helm charts, and we can use container images which are built with Nix, declaratively and reproducible. Let's first see what it looks like to write a Kubernetes manifest using just plain Nix. We would have some sort of variables like name and version, which be used throughout our Nix expression here. The write text function encapsulates the derivation and outputs a file, while the generators to YAML turns a Nix attribute set into a YAML string, which is then the payload for our pod YAML file. We can add some static data like API version and kind, and construct the metadata by inheriting the previously defined name. When defining spec containers, we can then again reuse this pattern and inject the name once more. With string manipulation, we can then construct the container's image URI based off the name and the version. The ports definition, to sum it up, would resemble again some static definitions. So this is already pretty neat. There's no templating of structures document involved. We can abstract and reuse common values like the name here. But this is ultimately just code that produces YAML, right? So the underlying process is still build, then hope. And here's the catch. There's no type safety. Let's say you make a mistake and accidentally set container port to the string 80 rather than an integer. So Nix would be perfectly happy to generate this YAML file, just like Helm template would, for instance. As you can see by the error message, this will also only break when passed to a downstream component like the Kubernetes API server. So this is where the OpenAPI specification comes in. It's a formal standard to describe HTTP APIs. As you can see in this excerpt here, Kubernetes, like many modern APIs, publishes a comprehensive OpenAPI specification that defines down to every property and field what a valid manifest would look like, including some types, descriptions, and which fields are required. In this specification, you can also find the nested values like the container port. Here, we can see, for instance, that this field needs to be indeed an integer and not a string. So wouldn't it be great if we can use this machine-readable contract to catch errors before they even reach the cluster? Well, that's actually what Kubenix does. By implementing Kubernetes OpenAPI specification, Kubenix enables Nix to validate your manifests during build time. The first benefit is actually that it reduces boilerplate code for us significantly. So let's revisit our pod example, but this time using Kubenix. Now we are importing the Kubenix Kubernetes module, which holds the complete Kubernetes API. Then we can conveniently start defining the pod's container. Kubenix takes care of setting the metadata name and also the container's name attribute accordingly to the name variable. Just like in the example before, we can then string manipulate and craft the image container's URI. So the corresponding definition of the port named HTTP would look like this. So the real win here is now we have time safety at build time. Say we make the same mistake as before, assigning the string 80 to the container port. We can see that Kubenix immediately tells you, hey, this should be a signed integer, not a string. You catch the error instantly right when you write the code, not at deploy time later on. So the same goes for other common pitfalls like unknown field names, invalid values, missing required keys, all are flagged up front. So far, we've only looked at some toy examples, a simple pod. But what about real applications? Let's see how Kubenix scales up to a full web application stack. Suppose we want to deploy Nginx. We set up our parameters like app, version, and port. We can now construct our labels based on these variables, similar to the first pure Nix example before. Again, we are importing Kubenix Kubernetes module, and now can define our resources. These consist of a deployment, a service, and an HTTP route. As you can see, everything is cleanly parameterized by our variables. There's no repetition. It's easy to extend later or override. Now, let's drill into each of these parts. First, the deployment. Here we can take advantage of the previously defined labels by specifying the match labels and then directly moving on to defining the template. Again, we're using the labels and inherit those into the metadata section. Similar to the previous example, we are defining the container's image URI and are done for the deployment. Pretty simple, right? Next up would be the service. Once we are using the labels as a selector to make sure that this service will select the appropriate pods from the deployment before. Defining ports is simple. We just inherit the port variable and specify that we are serving TCP traffic. Again, this code reads like a direct translation of what we want to accomplish. Finally, we set up the HTTP route. In other words, how the application is accessed publicly. This consists of a list of host names and rules. We want to match all paths, therefore we use this static rule here, and we then define our backend refs. Therefore, we are inheriting the previously defined port number and use the app variable to derive the name. So this makes sure that we are matching the service, which is already coupled to the deployment. As you can see, Kubenix doesn't just let you write YAML with Nix, it enables you to build, validate, compose whole application stacks in a way that's clean, reliable, and fully reproducible from end to end. Although Kubenix offers a powerful alternative to Helm's templating module, its creator recognized that Helm itself has grown to much more than a templating engine. So it's an ecosystem in its own, with thousands of ready-made charts for Kubernetes workloads. And with Kubenix, we can integrate them without any friction. How does this work? First, we simply import the Helm module provided by Kubenix. Then, in a fully declarative fashion, we specify our Helm release. In this example, we are installing Cilium as our container network interface. We start by using Kubenix built-in Helm fetcher, which references the chart's repo, name, and version, and pins it to a content hash to guarantee reproducibility. All Helm values can be defined in Nix directly, so customizing your deployment, such as enabling gateway API support in our use case here, is easy as updating a strongly typed config. So this approach means you can manage large, complex Helm values without mental overhead. With Helmfile, for instance, you would potentially even template these values, effectively adding just another layer of templating on top. But Kubenix doesn't just let you use Helm in isolation. So it allows you to even mix and match it with Helm releases, with your own custom Kubernetes resources, all in a single unified configuration. Therefore, let's revisit our example from before for one last time. So we import both now, Kubernetes and Helm modules from Kubenix, then define our Kubernetes resources as before, deployment, the service, and the HTTP route. And also, just like in the previous example, we would then define our Helm releases. For instance, our Cilium release, which is defined by a chart and some values. So the integration is seamless here. Kubenix merges all defined resources in a consolated manifest and even detects colliding resources at build time, so it prevents us from accidentally overwriting resources. So this means you can add your own custom functionality on top of third-party Helm charts. For example, to bridge gaps where a Helm chart doesn't quite fit your use cases. At the same time, we finally get a proper dependency management, right? So just like we have demonstrated with this gateway API example in Cilium here. Best of all, we are no longer bound to what the chart authors chose to expose via values. We are even not bound to the templating of the Helm chart itself. We can simply override any subset of generated resources on the Nix side. So, in short, Kubenix opens up the entire Helm chart ecosystem to you on your own terms. So, let's take a look what the workflow and toolchain looks like in practice. Once you define your Kubernetes workloads, using either pure Nix, just like before, or Kubenix, it's as straightforward as running Nix build. The build process produces a single output. This is a symlink called result, which points somewhere into the Nix store. Inside this file, you find a Kubernetes v1 list object, which contains all of our manifest neatly assembled. So if you want to inspect the output, you don't need any special tools. So just like, for instance, use JQ, and you can quickly visualize what resources are bundled there. You see summary of everything which is defined, like deployments, services, HTTP routes, and more. And when you're ready to apply your infrastructure, you can just hint over this file to kubectl. Kubernetes creates all the resources in one go. It's smooth, transparent, and most important, it integrates perfectly with familiar workflows. So the real power here, with Nix, we have one tool to build everything, from configuration to rendered manifest. In fact, Nix even gives us fully reproducible and pure builds. Everything can be tracked, versioned, and rebuilt identically perfectly for debugging and auditing. This property makes also the workflow very GitOps friendly, so if you like to roll this out for your team. Since Nix is very powerful, we can add arbitrary custom tooling to this process if it's needed, also without putting an extra burden on the developers. So in short, Nix and Kubenix turned this complicated puzzle of Kubernetes configuration management into a single, predictable, and developer-friendly pipeline. But why stop at just managing manifest? Wouldn't it be even better to build your own container images using the same unified toolchain? With Nix, we can do exactly that. So let me give you a quick taste. Here, how you would fully define and containerize Nginx within your stack. We start by pulling the desired Nginx version directly from Nix packages, which guarantees us that we always get the version we expected. Then we can define our container using build layered image, which is a fully deterministic and very efficient container image builder. For the container image, we inherit the name, and we would tag it then with our version. For the entry point, we are referencing the binary from the corresponding Nix packages package. And we would then, as well, to wrap it up, specify some common arguments. Finally, we're defining our Kubernetes pod. The image field references, again, like before, the previously defined container. So now we need to make sure that this URL will be served, but we can define now the entire stack with Nix. And here's where the end-to-end approach really shines. With all this precise composition, it unlocks a deep visibility and security for us. Let's say you want a full software bill of materials for your workloads. No problem. Just install this SBOM Nix with a single command, and you can generate a complete SBOM directly from this build output we've seen before. So you see everything down to the libraries, like glibc, just from the pod's manifest. And if you want to have like supply chain attestation, you get the provenance command line tool from the same package, and it's equally easy to generate a full SLSA provenance manifest, which documents exactly how and what dependencies your final artifact was built from. Again, we're seeing expected dependencies like glibc up to the Nginx binary, up to the Nginx container itself. And finally, for those who love a good visual, SBOM Nix projects also provides a command line tool to generate beautiful dependency graphs. So you can see it right before your eyes, every relationship. Your Kubernetes manifest points to a custom container image, and we see then all the packages that went into this container image, and also shared dependencies like the builder script. They are clearly mapped. There's no duplication, nothing is hidden. So it's a perfect illustration how the end-to-end approach works with Nix and Kubenix and makes everything reproducible. So let's recap what we explored. With Nix, we get a very powerful and flexible, purely functional, lazily evaluated language, which is purpose-built for system packaging. The language drives Nix packages, which offers a large and attractive ecosystem consisting of utility functionality and different system packages. With Kubenix, we can significantly reduce our boilerplate code, and it provides us true true type safety for Kubernetes, thanks to the OpenAPI specification. Furthermore, through its means of abstraction, it allows us to manage even complex stacks. It integrates well with existing ecosystems, such as Helm on the one hand and OCI containers on the other side. In my opinion, this unified approach represents the packagement solution for the platform to build platforms. And this brings me to the end of the presentation. If you like to go over the slides once more, feel free to scan this QR code here. As well, here's the GitHub project of Kubenix if you like to learn more about it. And at Sys11, we're building a software supply chain management system on basis of Nix. If you're interested in this product, feel free to scan this QR code here on the right side or come by our booth. So I'm now happy to answer some questions.
So let's maybe start from the top. The good thing is you were a bit early, let's say. Yeah. So we have 10 minutes for many questions. So let's start with the very first one. Does Kubenix support CRDs?
That's a yes and no. So it does support it by some means which is called custom types, where you can define the group version kind, basically, of what the CRDs would look like you're consuming. Unfortunately, at the moment, it does not support true type safety for the CRDs. There's a respective issue in the GitHub project, which you can find. So we might expect to see it in the near future. There are actually no technical blockers from also injecting custom OpenAPI specification into it, which is essentially like a CRD. Yeah.
Awesome. So it's always changing depending on the likes. So let's now go for, does Kubenix works in GitOps workflows like Argo CD or Flux?
It depends, I would say. So I haven't tried using it with Argo CD. So what I know is that Argo often relies on some Helm primitives as their package notion. So it might be, again, back to vanilla Helm charts there. So you might not gain much. But with Flux, you might be more lucky. But I personally would say that the tooling is very unopinionated. So whatever CI/CD pipeline you're running, it's fairly easy to just do this Nix build as I illustrated, and then you need to just like concentrate on actuating the resulting manifest.
Thank you. So we leave the great feedback just here forever, so you can always enjoy it. But coming back to CRDs, another question, can Kubenix use custom resource specs by reading CRDs from the cluster?
Unfortunately not, and I think it's not easily achievable. As you've seen by those hashes maybe, that's one of the caveats for reproducibility. You need to make sure that some remote resources matching the exacted output, and therefore there are always content hashes assigned to it. So there is actually no way of dynamically injecting those into it. It's actually one of the design principles of Nix, where you have to shift a lot towards the left side and often need to declare all the dependencies up front. Which introduces some sort of limitations. However, this is how we built our software catalog based on Kubenix. You can use a flake, and then you have all the inputs there. And then you basically delegate this content hashes to the flake log file, which logs those dependencies to a certain version. And from there on, the process is pure, thanks to the log file. And you can do this in a semi-automatic way, I would say. So you would rely on some sort of process which, like Renovate bot, to update CRDs from some sort of upstream vendor.
Great, thank you. Ranked very high. What about secrets? For example, SOPs encryption.
Yeah, so this is an interesting question because Nix has an interesting threat model. So basically, the threat model of Nix is that everything which goes through the Nix store, which is basically every resource you're touching, is actually in some sort of real-world state. So especially in particular, secrets needs to be treated somehow. And therefore, you can use SOPs. Actually, there's a project there's also a talk on the last NixCon from last weekend, which showcases this Nix SOPs. It should provide native understanding of SOPs for your Nix workloads. And other than that, for instance, we do some sort of managing the encryption on the tenant cluster side. So we are doing something like sealed secrets, but we wrote our own solution there.
Good, thank you. What about validating policies during manifest builds?
I would need to look into this. I don't think it's supported. I'm not sure. So if you see me around, feel free to approach me and we can dig into this. Yeah.
Cool. Is there integration with developer tools like LSP for completion of arguments in Kubenix?
Yes, I think there are several LSP servers out there for Nix. And also, they should then be available to Kubenix and give you a better developer support there, yeah?
Very cool. How do you specify which API version of a resource you are using?
That was a bit like hidden in my presentation slides. So these are the aliases, and I think they're pointing always to the latest available API version. If you would need, for instance, a V1 beta 1 cron job manifest, there's always a more verbose hierarchy introduced by Kubenix, which basically reassembles the API version, group version kind hierarchy structure. So yeah, this is possible.
Wonderful. So still 4 minutes for questions. We're really good. In Kubenix integration with Helm chart, the main point of validation is missed with OpenAPI schemas, which can be done via kubeconform? Question mark. I'm not really 100% sure. I see you neither. Maybe this person could maybe come by later and directly discuss with Arik. That might be a bit easier then. What about dependency management with Renovate, for example?
Yeah, we actually do this, and you can use Renovate. As I earlier outlined in the other question, we have all the dependencies as flag inputs, and those are like subject to renovation. And as a post command hook, we then simply run nix flag show, which will recompute the flag log file. However, since everything is at our end assembled in one large monorepository, which works that everything fits together somehow, it's still necessary that you have like good tests about it. We've, for instance, implemented some generic smoke tests, which use the Kubernetes API primitives. So basically, we actuate everything which undergoes our CI/CD pipeline in a K3s environment and make sure that all the pods are like in ready state after a certain amount of time, that every service endpoints are ready, and so on and so forth. So if you need to see a hands-on example, feel free to catch me. I'm happy to show this, how this works.
Great, thank you. So there's one question highly ranked when it comes to the releases. And in general, like, is the project still actively maintained? Because the last release is some while ago.
Yes, the project has undergone also a lot of forks in the later past. From my understanding, the project is still alive and kicking. This is also how I receive it from the community. But I think we're all lacking some contributions to it still. But yeah, I would consider it still open. It may also be some sort of in a realm where it's always served a certain process, and since it's just like implementing OpenAPI specification inside Nix, there are not that much of moving points, so it's reasonably generic already, and since for this reason it's also somewhat stable. Yeah.
Cool, we're coming now, unfortunately, to the last question, because then coffee break starts and we all want to have coffee. Does Kubenix also support installing an app and managing updates like Helm beyond kubectl apply?
I'm not sure what the notion of app is here, but managing updates would work just like the same with Helm, since everything boils down to this build process. One thing which needs to be taken into consideration is how you would then effectively delete resources which are not reflected in the latest revision. For example, at sys11 we built like a drift reconciler component, which is some sort of controller which actuates basically this manifest files, and they take track of like recent revision and make sure that those are removed. So it's doable, I would say, yeah.
Wonderful. And that's just directly 10:40. Thank you so much for answering all the questions. Yeah. So if your question, sorry, just some more talking and then you can collab. So if your question wasn't answered right now, please feel free to reach out to Arik. He will stay, as he mentioned. Now is the coffee break for 15 minutes. Then we will meet back, ideally here, of course, for Yussi's talk about dragons and Kubernetes. I'm really curious what that will be about. And now, a very huge thank you, Arik, for your talk. And now the great applause and clapping hands. Thank you.
Thank you very much.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.